I guess hope all of us are doing great. My name is Ernest, and this is Ernest Sciences and Mathematics TV channel. In this specific discussion, we are going to look at an aspect of the Cartesian coordinate system, and these are the differential elements. Later on, we are going to appreciate these specific aspects of our differential elements, especially in the topics which are going to be application areas in engineering and electromagnetics. And those, of course, are going to assist us try to interpret some of the various characteristics that we're going to encounter in that specific topic. So in this case, I'm going to use three illustrations to, of course, interpret this aspect of differential elements. And the three figures I've given on the board for A, B, and C are going to, of course, assist us achieve the same. So we are deciding the definition of coordinate systems that these are going to be reference, of course, aspects that are going to assist us try to define some vectors, or perhaps orientation of some of the vectors in three-dimension space for the Cartesian, the spherical and rectangular, or rather the cylindrical coordinate system. Now in this specific set, I'm going to use this first case. And before that, of course, there's a point that I want us to, of course, define so that we can be able to interpret, especially the figure P, which we are going to rely on heavily. So suppose we have a rectangular coordinate system that is defined by this axis of x, y, and z. We're going to see that for us to define a point that is normal to the zy direction, which is basically zy plane, which is basically the x, then therefore we're going to have a unit vector that is going to be given as ax. And we said that we can be able to have three services for these rectangular coordinate systems for x, y, and z. So therefore these are just surface elements which have been defined as dsx. And this is the surface element dsx is going to have this vector, unit vector pointing, of course, which is normal to the zy plane, and of course which I've indicated for a surface element dy dz, having this specific unit vector for this one x, which is normal. For the second surface element, we're going to have this a surface element that is going to have a unit vector y, which is radial perpendicular to the surface. And then therefore we're going to see that the plane is going to be formed, or the surface is going to be formed by this specific set of points, and this is going to be for the x and z, of course, which are going to have y as a normal unit vector given as such. And for the last part, which is a surface element for z, we're going to have this particular surface which is normal to the xy plane given as such. So we're going to have this one as a unit vector pointing outwards from that specific surface. So that's how we're going to visualize this specific second set of a point. Now from there, of course, we can be able to understand how these specific services are given in terms of their various, of course, axes for x, y, and z. Now suppose we have a point P, which is given as x, y, and z, and we have a specific or an increment in each of these coordinates for x, y, and z of a differential amount. We are going to obtain, or rather we can be able to have an increment in the x direction by dx, and then an increment in the y direction by dy, and an increment in the z direction by dz given as such. So these ones are going to lead to a new point, which is going to be P prime, which is going to be given using those various coordinates. So we're going to have a new point of x plus dx, and then another one for y plus dy, and the last one z plus dz as those new points over that specific point. Now the change from a P to P1 is going to give us a vector, which we're going to see later, which is a differential vector that is going to be of a length extending from this point. Just going to give that one using a different illustration. So this is going to extend from that point of this P to this one that is here. So this is going to be a differential vector, which is an elementary vector that is going to point from this point to A to P. We can be able to define different aspects of this increment for dx, dy, and dz direction. So the increment along this specific length from here to here is going to be along the y. So this is going to be dy, and the increment from this specific point to this one is going to be along the x direction. So this is going to be dx and the increment along this, of course, is going to be formed the dz increment, as we say. So these are going to assist us define this third point, basically, which means from our definition of the various points on the Cartesian systems, and therefore we're going to have the interaction of our new planes. The first planes of interaction are going to be having a point of intersection at P, and then for the new points, we're going to have planes interacting at the point P prime that I've given on the board. So therefore, we can be able to define this vector length from P to P prime, which of course is going to be illustrated using, can just be able to do away with this. So the new vector that is going to be realized, we can be able to denote it using dl, which is a vector of length. We can just give it just generally as that, which is going to be a vector that is going to be defined by these various points for dx ax plus dy ay, and of course we're going to just do away with this, plus dz az given as such. So this is going to give us a vector of a differential vector length being defined as this from this specific point to this one. So therefore, this particular change, an increment, is going to create what we call an interaction of these first three planes for P and the next three planes for P prime. And therefore, the 6 planes which are going to interact, of course, are going to give us what we call a volume, a differential volume that is going to be defined by what we refer to as a parallel pipe. And maybe write this. So the interaction of these 6 planes for the P and P prime, which are going to be, of course, surfaces, are going to create what we call a parallel pipe, which is a differential volume which is going to be achieved and illustrated as this first case that I've given for A in this particular aspect. So we can be able to define the distance from P to P1 by giving it as a magnitude of the dl that I've given as dl, and of course this is going to be given as so for us to find the magnitude of a vector, we can be able to give that one using the general formula that we done for dx, the square of dx given as such, plus the square of dy plus the square of dz given as such. So this is going to be the magnitude of the vector p prime given as dl respectively. So this vector is going to be given by this specific notation. And in any case, of course, if we try to look at this from a geometrical point of view, we can be able to find the volume, this differential volume that we have created, and of course, which is going to be a scalar quantity given as dv. So dv can be able to be defined as dx, dy, dz, which is a product of those 3 differentials given as such. And I've said that this is going to form a scalar quantity from that specific aspect. So for the differential surfaces that I've already explained for in these specific areas, there are going to be surface elements which can be able to be denoted as, or can be denoted as ds, which I've given for ds x, ds y, and ds z in that specific respect. So therefore, we can be able to define these differential vector surfaces which are being given for the ds x, whereby we are going to see that for dsx, this one we can be able to define it, and just to do away with this. So this dsx can be defined using this dy dz, and then we are going to have ax, which is going to be given as a vector which is normal to this specific surface element. And for the second one, for dsy, we are going to define it using dx, then dz, and then we're going to have ay as a vector element. And then lastly, we're going to have this vector for this surface element for dz, z, which is going to be given as dy, dx, and z given az given as such. So therefore, these are going to form the differential vector surfaces for this specific Cartesian coordinate system. And of course, these elements, as I've said, are going to play a vital role in various application areas, especially in the engineering fields of electromagnetics and other aspects. So catch us in our next videos. We're going to look at the other differential elements in the two spherical coordinate system and the cylindrical coordinate systems respectively. So that is it for now, guys. Bye. God bless.